And the stream is going, so now we're officially in action. So I sent you guys an email a few hours ago, and in case you haven't been on email since then, I wanted to point out that I put something up on the website this morning. For today, it's labeled Graphic for Three-Group Analysis for Example 4. It's an Excel spreadsheet that will allow us to take a more visual approach to understanding the idea of dummy coding for group differences. When in doubt, draw a picture, right? So that's what I'm trying to do. And since I'm a very bad drawer, I let Excel draw the picture for me. But before we get into that, I did have some requests to go over a few things from homework 3. So that, just to remind you, is due Monday evening. You should be able to do all of it. Things that I have helped people troubleshoot. So common sources of problems, centering variables. So when you're creating a new variable, let me pull up an example so that I'm not just talking into the land here. So I'm going to pull up example 3, which is the basis for the stuff I'm asking you to do in homework 3. And I'm going to scroll to the example where we're predicting income from centered education. Just point out the code and how that works. So in SAS, for example, this is how you center a predictor. It's the new variable that you're making equals the name of the old variable, and then whatever the centering constant is. And so in this case, you would need to subtract 12 in order to make 12 the new 0 point. So I've seen a few people who have had code where instead of having the centering constant at the end, they put a 0 in there. That would just create a duplicate of the variable that you already have, and so that wouldn't work. So make sure that the name you're creating to the left of the equals is a brand new variable name. So you need to change it to be different than the one that's already there. The way that I typically do that is to add the constant that we're centering with to the end. Then we have the original variable, and then we have the centering constant. And so that new variable, in this case, education 12, that's what goes into the model after the equal sign in SAS. The variable that goes before the equal sign is the outcome variable, the thing that's being predicted. So it would be fit count in the example 3 homework, and this would be please count in terms of homework 3 as well. And the same is true in Stata, with just a slight difference. In Stata, to make a new variable, you have the word gen in front of it, which stands for generate. There's no semicolons, but otherwise the structure is the same. It's the name of the new column equals the old column minus the centering constant. From there, the values that go into your lincom statements and into your estimate statements, these values are relative to the centered value. So for instance, because I've centered at 12, if I want to get the outcome variable that is predicted for somebody with an education level of 8, I have to enter -4 because 8 is 4 less than 12. So in the instructions that I gave you the actual values that I want you to create predicted outcomes for. So I think it was please count should be centered at 7, and I asked for a predicted outcome score if please count were 4 and if please count were 10. So keep in mind that that 4 and 10 have to be relative to the centering point of 7. So questions, what does lincom mean? Lincom stands for linear combination. So anytime that you want to make Stata do math that involves your fixed effects to estimate new quantities that are linear combinations of your intercepts and slopes, such as when predicting example outcomes, you can use lincom for that. There's also an analogous command called nlcom, which stands for nonlinear combination. And the analog to this in SAS is the estimate statement. And so the code looks similar, you just don't put in the pluses or the asterisks that imply multiplication. So any questions on any of that? Am I frozen? No, I'm okay, because everyone's looking down. And I thought, have they given up already? We just got here. Okay, so that much is okay? Okay, if you're having problems, remember the 15-minute rule. If you try to make it work for 15 minutes and it doesn't, stop and get help. It won't do you any good to just start plugging in values randomly into the homework. Because if you happen to get it right when you plug in something that's random, that's not going to help your cause for understanding how this works. So I would not advise that strategy. I also had questions about reconciling the differences between residual variance and parameter standard errors. So this goes back to the discussions that we had several weeks back in contrasting what standard deviation meant versus what standard error meant. Do you remember those terms? Okay, so they sound a lot alike, but they differ in their level of abstraction. So if I talk about the standard deviation of a quantitative variable, that is how far off, on average, any one case in my sample is from the sample's mean. So it's the cases relative to each other. Standard deviation conveys sort of the spread of the cases. This is a gesture one. How does standard deviation relate to variance? See if you remember this one. I'll take gestures. I'll take, yeah, square it. Yeah, variance is standard deviation squared. Standard deviation is the square root of variance, or if you're from the Midwest, the square root as an acceptable alternative. So residual variance is the same exact idea. The only difference is that rather than referring to all of the variance in an outcome, we're referring to the variability that is left over after it is predicted by another variable. So residual variance refers to the variance of the e's from the model. So how far off from the regression line each person's outcome is, that's the variability that remains. And so rather than thinking about how far off from the mean, it's how far off from the predicted outcome. The mean and the predicted outcome are one and the same if you're in an empty model. But otherwise, if you have predictors in your model, then the predicted outcome should be a better version than just the mean. And so we're going to look at today how to test how much better that actually is. But residual variance is the same idea as just regular variance, which is the squared version of standard deviation, which is talking about for an average case within the sample how far off they are. Okay, that much okay? I forget who asked the question, so whoever that was, make sure you nod or thumbs up me. Okay.
I have a question.
Yes. Go ahead.
Oh, never mind. My headphones aren't plugged in. Can you say that again about this, the standard error? Like, I'm just having trouble in the homework because the language doesn't align with any of the language that we've talked about in terms of options for what, like, the slope standard error versus the intercept slant standard error, and thinking about, like, as it relates to the population mean versus the population slope. Like, I can't tell what, because there's nothing about variance in any of those definitions, or nothing about like residual variance, or like I conceptually understand it, but the language doesn't make sense to me.
Okay. So standard errors and standard deviations both refer to an unsquared matrix. There is a squared version of standard deviation that is variance, and residual variance is what we pay attention to in the context of these models. There is a squared version of standard error, but that's not something that we've paid attention to. Just in case you're curious, the squared version of standard error corresponds to the sampling variance of an estimate. So you may see that term in other classes. But to try and help you reconcile what all of these things are, if we go back to just standard error of the mean, so the first instance of standard error that we found, that's not talking about a case within a sample. That's talking about one sample and how a quantity would vary across all the samples that come from a population. So in the case of the mean, the standard error of the mean is how far off any one sample's mean is from the population mean on average. So more generally, you can define any kind of standard error as how far off the sample's whatever is from the population whatever, where the word whatever is my technical way of referring to the parameter of interest. So the standard error of an intercept is how far off the sample's intercept is from the population version of what the intercept would be. The standard error of the slope is how far off on average that the slope from the sample would be from the population version of the slope. So the standard error is supposed to be a proxy for the expected inconsistency of what you got from your one sample. If you were to redo your study over and over again, what would happen across the samples? It's the expected offness, the expected deviation or discrepancy relative to the population.
Okay, and then the variance, residual variance is referring to the individual case. It's not general for the sample mean. Got it. Okay, thank you.
Yes, yes. So standard deviation and variance are talking about people. Standard errors are talking about samples. And so yes, I'm looking for you to be able to make that distinction. Are we talking about people offnesses or sample offnesses? And then are we in a squared metric or an unsquared metric? And yes, they are not given in the same way. So for whatever reason, when we pay attention to how well our model is doing in terms of how it's predicting outcome scores, we keep that scorecard, so to speak, in the metric of variance, in squared deviations. We don't talk about it in standard deviations, although we could. Whereas when we talk about standard errors, we keep it in the unsquared metric because that's what goes into the denominator of the t statistic. That's our hypothesis test. Okay, I think that's all the questions that I'm remembering from emails. Are there any others that I can talk about that would make things go better?
I have one question for
Yeah.
clarification on the Cohen's d. For the formula, the bottom part is degrees of freedom, and then it says DEN. Can you tell me what that stands for?
Denominator.
Okay.
So denominator degrees of freedom, let me scroll to see if I can find where D is in this example. So I know it's coming up here. There we go. Yes, so there's two different kinds of degrees of freedom. We've paid attention to one of them much more so, and that's the denominator one. That is the number for your sample size minus the number of fixed effects that are in your model. And so that one would be n minus k, and that's given in your output. Numerator degrees of freedom refers to how many slopes are in your model, and that's one that we're going to start talking about today in more detail. So if you're referring to a t, numerator degrees of freedom is automatically 1. Likewise, if you're referring to a z, numerator degrees of freedom is automatically 1. If you have a situation in which you would have more than one, then you would be using, instead of z, a chi-square, or instead of t, an f. And so we're going to meet our new best friend f today. All right, other questions?
So can you repeat that again, please? You said when we talk about standard deviations, it's sample
People.
a people versus the each case versus the mean, and then when we talk about standard error, it's the samples to the population.
Exactly.
And so the residual variance is that to the population then?
Residual variance is a people thing.
As a people thing. So it's like a standard deviation, like
the squared version of standard deviation, exactly. So okay. Let me get a picture up here that will help the idea of residual. So here, can you see the scatter plot that's on the right here? Okay, so when we initially defined variance, and I promised you that you wouldn't have to recall formulas, so I'll recall it for you because this one I've got. Variance is each case for the outcome minus the mean, square that, and we square it because some people will be above and some people will be below, and we don't want them to cancel. We sum those squared deviations, and then we divide by n minus 1. So if you, instead of saying each case minus the mean, it's the minus is the mean that is predicted from the regression line. So we would phrase that as a conditional mean. It's what is predicted for you based on, say, education in this case, or based on your group in the example that we started on Tuesday. So it's still the idea of how far off each person is from some sort of sample predicted value. In an empty model, the sample predicted value for everyone is the same number, it's the mean. But once we start putting in predictors, it's how far off are you from the mean that's predicted for you based on your predictor values. So how far off from the conditional mean. And so that idea that it's not all of the offnesses, it's the offnesses just from the regression line, that is the residual terminology coming into that. Because it's the e's specifically in the equation. Residual variance refers to the variance of these e's specifically, but it's still people. Okay, does that help?
I think what I'm getting confused is in the empty model, it's just predicting for each person, right? The y sub I is for each person. But when we talk about predictor, like when we add predictors to it, are we predicting for a sample population, or is like I get confused? Like, what are we predicting for? It's not a person, not individuals anymore, right? It's to the.
No, we are still predicting for individuals. So all we have is one sample.
Right.
Like that, like, unless you made up the data, right? You made up 100,000 fake people or something like that. But that's not what we do most of the time and not what you're learning this for. You only have one sample of people. So ultimately what we're trying to do is use this sample to see what predicts scores in the sample. And what we hope is that that result would generalize to other samples from the same population.
Okay, so it's just still for a single population, a single sample.
That's all we got.
Yeah, okay.
Right.
So the sample is the population then?
Not exactly. The sample is a subset of the population.
Yeah, okay. So we're making a generalization based on one sample. Is that?
Yes.
Okay.
Yes. There's a lot of hope that shows up in here, hope and belief that you just kind of have to, and there are, so the formulas for standard errors and such here, they rely on sort of asymptotic properties of sampling, like what would happen if you did the same thing over and over and over again. There are other ways to get standard errors that use only your sample, such as bootstrapping, for instance, which is when you take your sample and sample from your sample, and then you end up with something that's called an empirical standard error, meaning you're only referring to just your data to try and describe the wiggliness of your sample. All we have is the sample, but at the end of the day, what we're hoping to be able to do is to talk about what happens in the population. So that's why it's important to acknowledge that the results that we get are not going to be the exact same results if you did the study over and over again. We expect variability across samples. We expect sampling variability. And so the standard error is our way of anticipating what that variability across samples would be. Better? Worse?
A little bit better, but it's still unclear. So when we talk about the confidence level, it's not the same as the way we talk about confidence level, because it's not probability anymore. It's about how likely it's repeatable. Is that right?
Ish. Confidence intervals are really easy to screw up the interpretation because they're very non-intuitive what they tell you. A confidence interval is basically two standard errors around whatever you found. Like that's how you make it. What it's supposed to be is the percentage of samples in which the population version of your parameter would be found. That's what the definition is, and that's not a very useful definition. I will be the first to admit that. But the confidence interval is supposed to help convey the wiggliness across samples.
Okay.
A lot of journals are asking for confidence intervals around parameters, not just given the slope. I will give them if the journal wants them, and that's why I have included in the code the options that spit out the confidence intervals that go with it. I personally think it's more useful to give the standard error, because then you can make whatever level of confidence you feel like out of that. So I give the pieces that go into the interval rather than the interval itself. So I will always report whatever the estimate is, so like what the slope was, what the standard error was, and then depending on space, I may have a column for the p-values that go with it, or I may resort to stars if I'm running out of space to denote which ones are significant based on my alpha. Okay. So empty model versus predicted model. I wanted to pull this up to try and answer that question. So the idea of what residual variance means. So in the empty model, this is slide 2 of lecture 4. The empty model has an intercept in it. So everybody has the same predicted outcome given by the intercept, and that is the sample mean. So that's our worst case scenario in terms of prediction jumping off point. The variability of the E residuals, so how far off each person's actual outcome is from the one that's given just by the mean, the variability of those E residuals is the same thing as just what we used to call variance. It's all the variance that there is in the outcome, because this is another way of saying what the definition of variance is. Variance is how far off each case is from the sample mean. Beta 0 is the sample mean. So E is just the same thing as how far off each case is from the sample mean. So the variability of the E residuals from the empty model is all the variance that there is to be had. As we add predictors, rather than saying our best guess for each person is the sample mean, now we're saying our best guess is the regression line that we're creating from our model. The variability of those E's should go down. There should be less discrepancy across people because we have explained part of the reasons why people differed from each other. It's due to the model, not just whatever unknown reasons that are still left over that E is supposed to be representing. So in your output, it will be called residual variance, but it depends on the model what exactly that means. Residual with respect to what? If there's nothing in the model, the empty model, then it's all the variance. Once you start adding things, it's variance left over after the stuff you added. Any better? Not yet. You can be honest, it's okay. You won't hurt my feelings. This shit is hard. This is why I have a job. Any of that I can talk more about and make you feel better?
What are you doing this weekend?
Oh boy. You know, my weekends, not that I was super busy before, but each weekend I try to set a personal best for the fewest amount of steps taken on my Fitbit. I try to move just enough to make it think that I'm not dead, and usually finish a book while my son plays way too many video games because he's been in school all week and he hasn't had a lot of discretionary time. So yeah, that's what I'm gonna do this weekend. Does anyone else have any better plans they want to share? No. Yeah, doesn't that sound fun? Yay, parenting. We may be decorating pumpkins. Dad came home with some pumpkins from the store this morning, so we'll maybe doing that. Maybe eating a lot of Halloween candy. That may also be happening. Thanks for asking. Oh, so yeah, it's that point in the semester where we're getting tired, right? We can admit it. And I know that there is always some anxiety when people present you with information and you don't immediately follow it. I think there's a tendency on the part of graduate students in particular to ascribe that the blame lies with them, right? Like, why don't I understand this stuff? This must be something wrong with me. I'm never going to be able to get it. And it's like once those thoughts start seeping in, then no good can come of that. So let me reassure each of you that even if it seems hard right now, the more you fight through it, the more practice you get with it, the more repetition, the more exposure, and especially if you guys can start playing with data that you have access to, data that you care about, these things will start to sink in eventually. I promise you that. Each of you is capable of getting to the point where these things are more familiar and less scary. I honestly believe that. You just have to be willing to fight through the uncomfortable part where you feel like you don't know what's going on. Because guess what? You don't, because you just started learning this stuff. That's why you're here. It's okay that you don't know this. If you did know this, then this would be a waste of time. So I'm happy to try and clarify however I can. My job is to try and make this as easy as possible for you, but it's not going to be easy, no matter how good I were at explaining this. But it's going to be fun though, because when you finally learn how to make SAS or stata do what you want to do, and like that feels really good. So, all right. Do you want to see the thing I made you? Thank you. I hoped you'd want to see it. It's pictures. Yes, please. So let me pull that up here. So I wanted to show, hang on, let me get this more centered in the screen. 1 second here, got too many things open. Even though I need them all, which is why they're open. There we go. I made a picture. So this is the example that we were talking about in the context of lecture 4, showing you how to put in a predictor variable into these models that has more than 2 categories. So that's the general concept. We did 2 last time in example 3, and now we're ready to do 3, and I'll give you a chance to practice doing 4 in your homework. So the variables that go into the model were created right here. Can you all see this? Do I need to make it bigger, or is it okay? It's okay? All right. Let's see if I can make it just a scooch bigger. There we go. So the model itself is beta 0 as the intercept, plus this column that we made right here, which is supposed to capture the difference between, there's 3 groups, just to remind you, there's 3 different self-rated income classes, lower class, middle class, upper class, that people assign themselves to in the sample. And the first predictor here that I have named L versus M, because that's what it's going to mean, is designed to capture the difference between the low group and the middle group. And the second predictor is designed to then capture the difference between the low group and the high group. And the group that is coded 0 in both places is going to be our reference. So the results from the model are over here. And I have created predicted means as an example for each type of group. So these 3 numbers right here, these are your estimates. I will show you how to make SAS and stata give them to you, but that's going to be the number that shows up in the first column in your results. So this is these values are the ones that make the sums of the squared residuals So the numerator of the residual variance equation, the smallest. That's how they are found. This process of figuring out what each of these values should be more generally is called estimation, and this method of estimation is known as ordinary least squares. So it's the one that makes the squared residuals the least. That's what it's called. In other models, we will have more complicated methods of estimation necessary, but for right now, this one's fine. So I've entered those three values into these columns, and I have copied them down across the three rows because those three fixed effects are going to be responsible for creating all of the group information. So I have a column of ones here. I have the coded values for each of my groups, and then I have this column right here. So there's a formula in this column. That's how we created it. So I built this so that you could play with it. This is, and I sometimes make pictures in Excel just because it's easier to work with other people, but this is one of those things that is probably better done in software. I just wanted to give you something that we could play with together. So the predicted outcome for each person, if I'm in the lower group, is going to be the intercept times 1 plus the first slope that captures the difference between the lower and middle groups times 0 plus the second slope times the 0 in this column. And so when you work out that math, we get a predicted value of 13.65. And then the same thing would be true using the same coefficients, so the same fixed intercept and fixed slope values, but then replacing the values for the group-specific variables. And then the same thing in the last one here. So this is our linear model form. It's the idea of constant times variable plus constant times variable plus constant times variable, where the constants are the fixed effects. Uh-oh, can't highlight while I'm in the cell. Hang on. I do not want to accept this correction. Thank you. I just screwed up. Control Z, Control Z. Come on. Name. That's what happens when you tell it to do something that isn't mathematically possible. That's Excel's way of saying WTF. There, that's better. Okay. So what does this tell us then? Let me move to the picture that I created with this information. There we go. Now we can see it. So the y-axis is going to be predicted income, and the x-axis has each of my three groups. The x-axis is actually formed by two different variables, though. There's the L versus M variable and the L versus H variable. So in the L versus M variable, the lower group is coded 0 and the middle group is coded 1. So I know, based on the definition of an intercept, the intercept is always the expected outcome value when your predictors are 0. That given predictors being both 0 for the lower group, I know that the intercept is the mean for the lower group. So that starts me here at this, I've noted beta 0 equals 13.65. So the model directly gives me what the outcome mean is if I'm in the low group. That's my model intercept. The role of the other betas is then to get me from the low group to the other groups. So if I want to talk about going from lower to middle, I have a variable where lower is 0 and middle is 1. That is the red triangle here. So if I can get highlight on it. So I put the triangle in there to remind you that you've seen this sort of thing before, many, many years ago. This is algebra. Another definition of a slope is rise over run, the change in y over the change in x. So beta 1 is the rise part because the change in x is just a shift from 0 to 1. So we're moving from a value to 0 to a value of 1. That's a 1 unit change. The shift in the vertical axis, the y-axis, implied by that red triangle, is a difference of 8.8 854. So if I go from my starting point of 13 and some change, I go up 8.8, I get to here. And if I follow that over, that gets me to the mean for my middle group. So the slope itself tells me for every unit change in x, what is the change in y? Given my coding scheme, a unit change in x corresponds to the difference between low and middle. So the model is giving me what is the mean for low, how much higher the mean for medium is, and that gets me to the 22.5. Okay. How does that sit? I'm changing up my my questions here. Rather than asking how we doing, I'm going to say how does that sit? Because it is a slope. It's not the same kind of slope as, let me pull back the picture in here. Like when we talk about education, right? There's a slope. I have a slope that goes from 0 to 1 on the x-axis, but it's still a slope. It's just harder to think about the idea of a slope corresponding to a change in group, but that's what I'm doing. I'm leveraging the same technology to talk about group differences. So the points of the triangles are the means for those predictors. The points of the triangles are the means of the outcome for each unique group. I have 3 unique groups. Therefore, I have a mean for each group. I need 3 means. And the model's job is to give those to me. So yeah, the means for the groups, that's what I calculated up here as the y-hat. The model gives those to me. What we're trying to figure out is what the model parameters mean and how they get those. So the intercept is my low group because I coded both predictor variables 0. Beta 1 gives me the shift in y corresponding to a change from the low group to the middle group. That's the 8.8. So if I go from the low group to the middle group, if I add together the starting point for low, which is the 13, plus the shift going from low to medium, that gets me to the 22. So that's just low versus medium. So let's set, or middle. Let's set middle aside. Now the other predictor. I've called this one low versus, I didn't want to call it low versus high. I want to call it low versus upper. You can tell I went back and forth on what I called these things, and there we go. Make those U's to be consistent with upper, but it's the highest of the 3 groups is the idea. This slope is trying to get us from the low group to the upper group. So I'm still starting at the same place. I'm still starting at what is low. And now beta 2's job is to tell me what is the change in y corresponding to a 1 unit change in my new x, where my new x is this L versus U column right here. So I got to go all the way from here, low group, up to upper group. And if I go from low, the 13, plus the difference between low and high, that's the 11, that gets me to the 24. So the slopes, the beta 1s and the beta 2s here, there's still the change in y for a 1 unit change in x. A 1 unit change in x corresponds to a shift between one group to the other. The low group to the middle for the first predictor, the low group to the upper for the second predictor. So the model directly tells me whether or not middle is different than low, and that one was significant, and whether upper is different than low, and that one was significant. Now the one that's implied, the one that you would have to ask for as a linear combination, because it's in there, but it's indirect. So this is where you would need an estimate statement in SAS or a lincom statement in Stata, is to get the difference between these two triangles. So blue minus red gives me purple, because I love color and why not? So blue minus red gives me this purple. The difference between these two triangles on the y-axis, that's 2.1, and that's the difference between the middle group mean of 22 and the upper mean of 24. Because if I can get from low to middle and I can get from low to upper, then the difference between those two gets me from middle to upper. And so I have to ask for that one separately. Okay. Does this help at all? Pictures. Okay, I'll take an ambivalent shrug. I'll take that. Because the worst I can do is not try, right? The best I can do is try and not fail. So what questions do you have about how this works? Farhan has a question. Do you want to talk or type?
Yeah, so just to review everything, um, the slope of the line connecting the means, right? That's going to be our beta for each group, each dummy variable, right?
Yes.
So you drew those vertical and horizontal lines so we can see the rise over run relationship easier.
Yes.
And can you explain the part after that again? The um, where you like compare both the horizontal lines, and you said we find the difference between the blue and the red triangle.
Mm-hmm. So to get the mean difference between upper and middle, that's implied by the model, but it's not given directly. If I know how to get to 24, I know how to get up to this because it's beta 0 plus the difference of 10 that gets me up here. And I know how to get to the 22 because that's beta 0 plus the 8 that gets me up here. What I'm asking for is the difference between 22 and 24. That's not given to me directly as a slope, but I know based on the slopes that are given to me that that difference should be 2.1 because
Yeah,
it's this remaining
it's that gap
difference.
between the blue and the red line, right?
Yes, it's the difference in the y-axis between the blue and the red triangles.
So you'd subtract the two slopes.
I would subtract beta 1 from beta 2.
Okay.
Beta 2 minus beta 1 gives me the difference of middle versus upper.
Okay. Hang on. I can think of this in terms of if you think of bar plots, right?
Mm-hmm.
So think of like the intercept being here, and beta 1 would be how far up the, let's say, the middle group is from that intercept. So it's going to be
Yep.
here somewhere.
Mm-hmm.
So that's beta 1, right?
Yeah, so if
And
this is your intercept, beta 1 is this.
yeah, and beta 2 would be the distance between that intercept
Between this,
and the third group.
yeah, I'm out of hands, but yeah,
Yeah, something like that.
yeah.
So if you want to find that the gap between this guy here,
Yeah,
the
so this
group,
and
and the
this.
second one, sorry,
Here, I
yeah,
think I got it. Okay, the intercept is my thumbs, and this is
okay,
beta 1, and this is beta 2.
Yeah.
And I want this.
Yeah, that distance between both your index fingers.
Yes. Or yeah, I'm flipping you off accidentally. Okay. All right, there we go. The distance between
Okay.
my middle fingers. Beta 2
Yep.
minus beta 1 closes that distance.
So that would give you the difference between group 3 and group 2.
Yes.
Okay.
Yep.
Okay. Thanks. Thank you.
Sure. All right, I'm of two minds as to where I could go to make this better, is to show you what would happen if we rearranged the model. Because sometimes I feel like that helps if you see another instance of it, like what these things are doing. But I also think that could make it worse because then it's a potential way of confusing what is going on. So I could either do that or I could show you how to make SAS and Stata do this stuff for you. The latter? Okay. So in order to do that, though, I got to go through one more part, but I can show you where these numbers in particular came from. So let me pull up example 4, and then we'll look at where those numbers came from, and then we'll look at the rest of the test of fixed effects. So this is example 4. This is one of the few instances in which I put SAS and Stata code in the lecture and in the example because it's something that I thought would be helpful to have it in both places. So it is redundant, but that was deliberate. So we're still playing with the same data from the general social survey. The first step is always tell it where your data is stored, where's the folder location. Then I have code to import it in Excel. We're going to be working with 2 different categorical variables in this example. One of them is what you've just seen as working class, and another is an ordinal variable for how happy you are. We're also going to be working with age in years, years of education, and income is the outcome we'll be predicting. And so then I'm labeling all the variables, applying the value labels so that the categories will show up on our output when we ask for descriptives, and then selecting cases that have all of those as well. And then Stata, folks, same idea. First step is to tell it where your folder is that stores the data file. The import then brings it in. Label define is labeling the values of the categorical variables for class and happy. And then we have labels for the variables themselves, adding those categorical value labels, and then selecting complete cases. So you've seen all of this before. I just customize it in each example to have only the variables that we're going to be working with specifically. Okay. So first thing, a review. Empty model. So proc means here is used to get descriptive information for quantitative variables. The same thing is true in Stata for the command summarize. And in this example, I'm only showing SAS output because the two are going to be almost exactly the same. But if you wanted to see what it looks like in Stata, there is a log file, .log, that you can open up. It's just plain text, and you can see exactly what the Stata output looks like. So the mean of income is 17.3. So that's $17,000 for your average person. Standard deviation for income, is that a people thing or a sample thing? Yeah, we'll go back to familiar territory. People thing, yes. So on average, your average person is off from that mean of 17 by $13,000. So that describes the variability in income. If I take that 13 and square it, I get the next column, which is variance. So you can think of 190 as a numerical estimate of all of the reasons why some people make more money than others. Like that's the differences between people that we're going to try to predict. And so income ranges from just $200 all the way up to almost $69,000 in the sample. Going to make a picture. This is what income looks like. Even though it's positively skewed, I have no problem fitting a general linear model to it because it's not about the distribution of income marginally by itself. It's about what it looks like in terms of the residuals, which we will find out after we fit a bunch of models. Here is my empty model. So if I just start with the intercept, so each person gets the sample mean as their predicted value, the role of the empty model is to spit back the descriptive information that I just showed you. So my residual variance from the empty model is the same 190 that proc means just gave me. All of the variability in the outcome variable lies in the E residuals right now because there's no predictors in the model yet. Likewise, what each person is predicted to have is the 17. That's my fixed intercept, that's my sample mean. If I were to then put in my working class variable, so step 1, I got to find out how many groups I have to know how to put it in the model. So this is something that you know how to do. Do you remember proc freq and tabulate? That's how we get descriptive information for categorical variables. It gives you frequencies and percentages. So I'm doing proc freq for work class and SAS, as well as tabulate for work class and stata. And here are my percentages. So I know that most of the people reported themselves of being lower class, about 60%. 38% reported themselves as being middle, and only just under 3% reported themselves as upper class. So this difference in sample size is going to show up in our results. The comparisons that involve this upper group are going to have much higher standard errors. Because the smaller your sample, the more wiggly or inconsistent your results are expected to be. So here's the dummy coding. So in each program, I'm starting with 2 new blank variables. So how did I know that I needed to make 2? Yeah, I'll take hand gestures because I got 3 groups. So if I were to have 4 groups, how many new variables do I need? I need 3. So there's your first tip for homework 4. The homeworks will also tell you who I want to be your reference group. Now you can pick whichever group you want for your reference group in your life. It doesn't matter. It's a choice of interpretational convenience. The lowest group is what I picked here. It's also the one that's most frequent, so that makes sense as a reference group. In order to create a reference group, that is the point at which all of your new predictor variables have to have zeros. So both new predictor variables, in this case, all 3 with respect to homework 4. So
Could you say that just one more time?
sure. Highlight these 2. In order to create a reference group, so in your instructions, for instance, I'll tell you to put the control group as the reference. What I am saying is zero out that group in your new variables. What that's going to do is cause the model intercept to become the mean for that group, because the intercept is the expected outcome when all your predictors are 0. So you're saying your expected outcome when all your predictors are 0 is your reference group, the reference you are here assigned for your model. So that's why group 1 is zeroed out for each of my new predictors when work class equals 1 in both of these programs. The first non-zero condition then shows up for work class equals 2. And the way that you can think of this, these zeros and ones, think of them as like switches, like light switches. So I want to turn on this first variable when work class equals 2. That way, that variable is going to get me from my reference group to the group coded 1. Likewise, I'm going to turn on the second predictor, set it to 1, if work class equals 3. And everything else gets set to 0. Okay, does that make sense? Maybe. So how would this need to differ if you had 4 groups? We got to make 3 new variables, right? Well, I would have to do the same idea. I would have a third new variable that I'm creating that would turn on if I'm talking about group 4. So the first new variable turns on if it's group 2. The second new variable turns on if it's group 3. And if I had one more in here, so I would have to put another one here, here, and here. Let's say that I have a group 4, so I'll just say something like L versus 4 equals what would go here? Yeah, I need a 0. It has to be 0 because I still want low to be my reference group. So low is zeroed out all the way across. And I don't want this turned on yet if I'm talking about group 2. I don't want this turned on yet if I'm talking about group 3. So if I have a fourth group, I would need another row of code that says if it's group 4, then it would be 0, 0, 0, 0, 0, 1. So I'll give you a chance to practice that in homework 4 because it's designed to look very similar to this one. Okay, so questions on coding. All right, then here's my model. So the y-hat, they're that linear combination of intercept plus slope times variable plus slope times variable. That's what gets me the mean for each group. So then I've shown you using that model how it would create each of the combinations. So if it's the low group, the values that go into this are exactly the same values that you use to create the variables up here. Let me get rid of this so that I don't forget and have this be wrong. So if I fill in a 0 in both places, that basically kicks the slopes out. The low group's mean is nothing but the intercept. If I'm talking about the middle group, they start with an intercept because everybody starts with an intercept. I turn on beta 1. Beta 2 is still off. Likewise, if I'm talking about the upper group, they get an intercept. Beta 1 is still turned off. Beta 2 is turned on. And question, so 0 is on all variables in our model if we want the intercept. Yes, so the group is the reference if all of its predictors are zeroed out. Otherwise, a 1 on the variable whose mean we want with the others being 0, correct. So if we've got a fixed intercept as our baseline, then these 1s move us from the reference group to that other group. So the betas then capture the shift. There we go. So the things that will be provided directly by the model are 3 of the 6 here. So if all you do is put in your 2 new predictors. So income is the outcome variable equals the 2 new predictors. Stata code looks very much the same. Income is the first word. It's always the outcome variable listed first, followed by your 2 predictors with C dot in front of them so that you can do math on them. If that's all that you put in, then what you'll get back are just the 3 things that you asked for. So the fixed intercept, given our coding scheme, that's the mean for the low group. L versus M was set to 1 if we're talking about the middle group. So 8 is the difference of low versus middle, getting from the reference up to the second group. Likewise, L versus U is turned on if we're talking about the third group relative to the reference, and so 10 is how much higher the third group is from the first group. So we're missing some stuff. We don't know if the middle 2 groups are different from each other. We don't know M versus U. Now I can look at these, and based on my finger math, the difference between my fingers, or alternatively, the difference between my 2 triangles on the y-axis, that difference, that I don't have yet. That has to be an estimate statement. So the extra things that I asked for show up in a separate table. This table is what is created by the estimate statements here or the lincom statements in Stata. So there's more statements here than what you actually need because I wanted to write them all out. So here's my advice to you guys. Have you ever done something that took a lot of concentration and effort, and you figured something out, and then you moved away and you came back like 6 months later and you looked at it and you're like, I have no idea what this is. I have no memory of ever having done this, but this is clearly my handwriting or this is clearly my typing. I've like a ghost took over my body and figured this out and I have no memory. Yes, stats, exactly, myself included. So to avoid that, think of these estimate statements and these lincoms as your trail of breadcrumbs to your future self. Because you know how hard you're working right now to figure out what beta 1 and beta 2 mean? Do you want to redo that in 6 months' time? No, you don't. So do the figuring out now and leave yourself a trail. So the figuring out here is the idea of writing out what the model says each of these terms is going to be. So the model says the mean for the low group is, beta 0, so intercept 1, plus no beta 1, because that was coded 0, and no beta 2. Likewise, the middle group is intercept 1, and a 1 for the first variable where it turned on, and the mean for the last group is a 1 for the last variable. So now you've got what the mean is for each group. You can literally subtract these lines of code to figure out how to get the mean difference. So if I want to do low versus mid, I start with this line right here and subtract from it the line above. So if I work from left to right, what is 1 minus 1? Checking to see if you guys are still here. We got that one, 0, yeah. So the intercept drops. Okay. What is 1 minus 0? We got that one. That shows up right here. What is 0 minus 0? 0. So that's created that line. Likewise, if I start with the upper one and try to subtract the low, 1 minus 1 is 0, so the intercept drops. 0 minus 0 is 0, and 1 minus 0 is 1, so that gets me this line. Now the one that's not given by the model is upper versus middle. So let's start with upper and subtract the line above it. 1 minus 1, still 0. Intercept drops. 0 minus 1, here's a tricky one. 0 minus 1. Yeah, minus 1, the negative 1. That's why that's there. And then 1 minus 0, positive 1. That's why that's there.
So you're subtracting, you're taking the one on the bottom and subtracting it from the top. Okay.
Yep. And if you did it the opposite way, for instance, if you did this, you would get the exact same number, but a different sign. Because it's which one is your anchor and which one are you moving to. So the one that has the negative 1 is your reference, and you're moving from the minus 1 to the 1. So that's why I'm labeling these things in a very particular pattern. And when you do your homework, I'm asking for the same pattern. Which is the reference and which is the one you're moving to? And so even though, like this low mean right here, that's nothing more than the intercept. And even though these two differences right here, low versus middle and low versus upper, those are nothing more than the slopes. Going to the trouble to actually write this out means that you have a labeled piece of output that you can then interpret 6 months from now, right? This is this difference. This is that difference. It's very comforting to come back to this. It's much less comforting to come back to something that looks like this table right here, right? Beta 1. What's beta 1? Well, QED. What is it? It's obvious now, but it may not be obvious later. So yeah, these estimate statements are your trail of breadcrumbs to help yourself later. So if you had a fourth group, then you would have another row here for the fourth mean, and you would actually end up with another 3 mean differences by taking the fourth row minus the second, the fourth row minus the third, and the fourth row minus the first. Okay. And pictures are the next part. All right, how are we doing? Yes, okay. The head moves side to side. We're a little more enthusiastic, so I'll take that as progress. I will take that. Here's some pictures. So the idea of whether or not we can believe in these results, it turns out that if the assumptions of your model are not plausible, then it's the standard errors that are problematic. Standard errors and p-values. So I wanted to show you some of the pictures that are going to show up that speak to whether or not it's reasonable that these residuals are normally distributed, are independent of each other, and have constant variance. So the first picture here is a histogram of the E residuals. You can think of these as all of the differences that remain within each group. So the model is saying that each group has the same amount of residual variance. This plot next to it, this is what's known as a QQ plot. I didn't show you these earlier because I personally find them very difficult to interpret. but you will see these for different kinds of distributions. If the distribution is what it's supposed to be, then all the scatter points will be on the line. If it's not, they get off the line. If we compare the blue line to the red line here, the blue line is what it's supposed to be as normal, and the red line is the best fit to the data. There's too few cases on the left side, and there's too many cases on the right side relative to normal. And that is a direct consequence of the fact that this outcome is actually bounded. It stops at 0. It's positively skewed. So normality is not like super great. This would give me just a little bit of pause. It's one of those things where it's like, okay, this is plausible. I can work with it because there's more stuff that we're going to add to the model. Here is residuals for each group, and it looks like in the lower group there may be less variability left over than in the other two. And so we might potentially want to do something about that, but not in this class. That's another class, unfortunately. Okay. Standardized estimates. Do you guys remember those? Standardized slopes? Yeah, so I have code here using procreg to get standardized slopes. They recast these slopes into a correlation metric ranging from -1 to 1. And for mean differences, though, it's probably more useful to get D's. Cohen's D's are standardized mean differences. And so I asked for those from SAS specifically. So I did some math on the saved estimates to compute those. That's not something I'm going to ask you to do, but it is something that's very handy to do in SAS. And here is the results section that would describe all of these analyses. There's one part that we haven't talked about yet, and that's right here, our friend F. So that part is the one thing that we have left for this section. Then we get to try something else. Okay. Questions before we wrap up for today? Nope. Okay. Then let us call it a day. Let me know if I can help. If you have any questions over email, or if you want to chat, office hours or later. Otherwise, have a good weekend. Carve some pumpkins.